here we are doing horizontal transformations. So the first thing we need to talk about is horizontal shifts. Now the interesting thing about horizontal shifts is they always go the opposite direction of the number, and it's also always an inside number that's affecting x. So you can see our f of x plus 2, that plus 2 is added on the inside of the function instead of the outside. And that actually causes the graph to move left 2, even though it's a plus 2. I want to show you why, and this is a little bit tricky to explain, but remember our function for each of these points, our function is f of x, so f of 0 equals 1, right? And f of 4 equals 3, and f of 2 also equals 3. And then last we have f of 5, which equals 5. Okay, so we're keeping the y values the same because it's just y equals this. It's the x values that are changing this time. So think through this with me. What number do I need to add 2 to get these numbers? So for example, so let's kind of rewrite this in this form. So instead of f of x, we're going to have f of a number plus 2, and we want that to equal f of 0 so that it equals 1, because the value of the function of at 0 is 1. And so what number would we plug in here to make this value 0? Well, the answer to that would be negative 2, right? So that number there would need to be negative 2, so that's f of negative 2 plus 2 would be f of 0, which is 1. Based on the definition, this graph tells us f of 0 is 1. So in order for that to be true, when we add 2 in there, that means we need to change that x value to a negative 2. So that gives us a point at x equals negative 2, y equals 1. So that's that first point right here. Same thing, we need f of 4. So f of what value? Just use a weird symbol for it. What value plus 2 is going to give us f of 4, which is going to equal 3? Well, the value we need has to be 2 to make this true. So we are going to do our point at 2, 3. The y value is staying the same. The x value is changing so that the definition for this function stays the same. So we need a 2 in order to do f of 4, which is 3, so that gives us a point at 2, 3. Let's check this. So 2, 3 is right here. Then we have this point, f of 2 equals 3 would be 0 plus 2 in order to equal f of 2, which is 2. So that means we're looking at this number for our x value. So that would be at 0 for x, and 3, sorry, f of 2 is 3, not 2. So that's this point right here at 0, 3. And then lastly, f of 5, so we need the value of f, sorry, my f looks funky, f of something plus 2, which is f of 5, and f of 5, of course, gives us a value of 5. So what number did we put in here? We put a 3. So that gives us the point 3 for our x value, 5 for that y value. So by putting that 2 inside that function, it means we have to adjust the x values the opposite direction for the function rule to be correct. So that is why our graph will move the opposite direction in this case to the left. I hope that's helpful. I did kind of throw this together for one of our students after class who questioned the left-right thing as well. And so we practiced this whole thing with a parabola, we said let's let y equals x squared. I didn't quite color code everything like I should have, so this should have been red to match up with our graph properly. And then this would be our new version of this. This would all be blue to match up with the blue graph. And then we have this one, which is the green graph. And I was getting a little lost as I was doing that problem, but I realized later that the reason I was counting wrong is we're counting from 0 each time. So let's look through this. So this is at a 3. This point right here is at -1. The vertex of our parabola, of course, is at 0. So here's our basic parabola graph. We add 1 to it. So to get these numbers, what I did is I plugged in the numbers. So I went from the same numbers I did with my red graph, -2 to 2. So -2, plug it in, I get -1, -1 squared is 1, -1 plus 1 is 0, 0 squared is 0, 0 plus 1 is 1, 1 squared is 1, 1 plus 1 is 2, 2 squared is 4, 2 plus 1 is 3, 3 squared is 9. So when we went through and graphed these points, we ended up getting this parabola here, which is moved to the left one, even though it has a +1. Then in the green one, I did a -3, and I did exactly the same thing otherwise with taking the numbers from -2 to 2 and plugging those in. So -2 minus 3 is -5 squared is 25, -1 minus 3 is -4 squared is 16, 0 minus 3 is -3 squared is 9, 1 minus 3 is -2 squared is 4, 2 minus 3 is -1 squared, which is 1. That didn't really give us a whole complete picture, so then I kept going. 3 minus 3 is 0, 0 squared is 0. Let's go ahead and do 4 minus 3 is 1, 1 squared is 1. So that gives us this graph here. We can now see that we still have that same parabola, but it's moved from its original point at 0, 0 to a point at 3, 0. Or in other words, it has moved to the right 3. Okay, the other thing is horizontal reflections. So to indicate a horizontal reflection, we have a negative inside the function, like the x is negative instead of the outside of the function being negative. So an inside negative, that would be like if we had something like y equals -x squared. However, something like that's not affected by this rule because it is symmetric on the y-axis, which means if we flip it over the y-axis, we still have the same picture because it's symmetric. As you can see, this graph would be -x squared turns it back into a +x squared. So it's exactly the same graph. So it's easier when you're doing problems like this to use something like a square root or something that, or a logarithm, to make it more obvious as to what's happening. Anyway, here's our basic example we've been doing. We have all of our same numbers. We're just going to take those x values and switch them because we need them to be these numbers. If we put a negative there, we then have to plug negative numbers in order to get these numbers back out. So we're plugging in negative x values because of that negative to get these same numbers to get our same y values. So the result is that the picture is flipped over the y-axis, even though it's the same exact graph, otherwise same shape and size. Okay, so horizontal scalings are the really weird ones, and I think I already created its own video during class, and I didn't really stop to explain why this happens, but it's the same idea. Instead of the 2 multiplying times an x to get a new value that we're plugging into the function to then get y, we are attempting to get these same x values. So if we want f of 0, we need to plug in f of 2 times 0 to get that, right? That doesn't really change anything. But then for the next point, if we want f of 2, we need to plug in 1 times 2 to get that same value. So that's our x value now because we have x times 2, which gives us 2, and then it corresponds to this point so that the answer is 3. So the point that gets graphed is instead of at 2, 3, it's at 1, 3 because it's kind of like the opposite because we're trying to get to that x value that we plug in to get that y value. So that's why we have this point at 1, 3. Same idea on each of these. So if we have f of 4, we're going to get that by going f of 2 times 2. And so that would give us a point at 2, 3 instead of at 4, 3. So the original number was 4, 3, but because we are changing it to a 2x, we need it to be a 2 times 2 to get the 4. So the point's at 2, 3. And then to get f of 5, we would need to do f of 2.5 times 2 to get that same y value. So that's why we get that point at 2.5 comma 5. So everything with horizontal is kind of opposites, and that's because instead of the value just being affected like the y values are vertically, it's going backwards to affect it to get it back to the numbers that are defined. Hopefully I haven't confused the issue more than I already did, but I feel like maybe that's a little clearer than what I did in class. So I hope it helps. Thanks. So maybe I will just jump in and do this one really fast. We kind of avoided it earlier. I need to run to an appointment, so I'm not going to do this one right now. We will still double check this one at the beginning of class next time. And then we have our math disco on Thursday. So be sure to tune in from home if you are there learning. Thanks.